2. Okay, so today we'll be going over the practice exam 2 for organic chemistry. So we've been provided a periodic table just as a general reference. And now what we're asked in this first question is to identify the configuration at each stereocenter for the following molecule. Okay. So I'm going to draw out all my hydrogens. Okay. So one trick that I'm going to use is I'm going to take this molecule and I'm going to rotate it 180 degrees. I'm just going to flip it upside down like a pancake. So we're essentially rotating it along this axis. And my goal in this process to assign the stereochemistry at each center is to set it up so I have my hydrogen in the back. Okay, so I'm going to start with each of my carbons in this first structure with hydrogen in the back. And I'm going to assign priority. So as we see at our first step out, we have 2 carbons and 2 hydrogens, 2 carbons and 2 hydrogens, and 3 carbons and a hydrogen. So which group is priority 1? The top, the left, or the right? Which group is priority 1? The top. So we're going to put a 1 there. Okay, next we're going to go another step out for our tiebreaker. We have an oxygen and 2 carbons, and we have 2 carbons and 2 hydrogens. What wins out? The right or the left? The right, yep. So the right is priority 2, the left is priority 3. We draw our arrow, and as we see, it's clockwise from highest to lowest priority. So what will we assign this stereocenter? R or S? R, yep. So the first stereocenter is R. Okay, now, just to make sure that we understand that when we flip this molecule, this carbon ends up here, okay? So let's look at this next carbon in our flipped structure. So looking and counting, we see this top group has 3 carbons and a hydrogen. This bottom group has 2 carbons and 2 hydrogens, 2 carbons and 2 hydrogens. So which group is higher priority, top, left, or right? Top, yep. So that would be priority number 1. Okay, now we go one more step out. So we have 3 carbons and a hydrogen versus 2 carbons and 2 hydrogens. So which group is higher priority, left or right? Right, yep. So that would be priority 2 and priority 3. So we trace our arrow from highest to lowest priority, and that looks like an R stereocenter to me. Does that make sense to everyone? So this center we'd assign as R. Does that process make sense? Any questions on that logic? Okay, let's keep going then. So let's look at this stereocenter next. So assigning priority. So at our first carbon center out, we have an oxygen, 2 carbons, and a hydrogen, compared to a carbon and 2 hydrogens, and a carbon, and two hydrogens. So which group is highest priority? The bottom group. Yep, so we assign this as priority 1. Now we're going to go another step out. We're going to go another step out. So we have 2 oxygens and 2 carbons versus 3 carbons and a hydrogen. What is higher priority, oxygen or carbon? Oxygen. So the group on the right is next highest, and the group on the left is the lowest. We trace from highest to lowest priority, and what would we call this center as we're going counterclockwise from priority 1 to 3? That center would be S. Does that make sense to everyone? Does that make sense to everyone? Perfect. Now for our last center, right here, which corresponds to this carbon right here, because we rotated 180 degrees, just like sort of turning over a pancake. So oxygen is highest priority. And now looking at our next 2 atoms, we have a carbon attached to 3 carbons and a hydrogen versus 2 carbons and 2 hydrogens. So which group is highest priority, the bottom or the left group? Which group is higher priority, the bottom or the left group? The bottom, yep. And the left group is priority 3. So now tracing from highest to lowest priority, we're going clockwise. So what is the center going to be? R. Now, just for those curious, you can check your work by inputting a structure into Marvin Sketch. Give it a moment to load up. I just want to show this because it really is just another tool you can use to check your work. Though I find that this method of checking is only particularly useful if you're experienced with the structure in question. You have to be somewhat familiar with the naming conventions in order to effectively utilize. So we can draw out the structure in Marvin Sketch. Okay. Now let's add our oxygens. Okay, looks good. And now what we do is we highlight the structure, we go to structure, insert, IUPAC name. Okay, and we see it's 3S, 4AR, 8AR, 9AR, 4A, 8A, dime. Oh, that should not be a methyl, that should be a hydrogen. These should be hydrogens. One moment. I'm going to need to close this down and reopen it. One moment. Sorry about that. Sometimes Marvin Sketch gets confused when you ask it to name a structure. One moment, let me reopen Marvin Sketch because I do want to show you how this works as a means of checking your work. Okay, so if you pull open Marvin Sketch and you copy and paste your structure, you have to make sure your structure is drawn accurately. Okay, you go to insert IUPAC name, and it will go through and name the compound and assign the stereochemistry at each stereocenter. Though it takes it a moment, here we go. So we have 3AS, 4AR, 8AR, 9AR, dodecahydro, 2,3B, furan, 2-O. Now, of course, you'd have to, this name is too complex to dissect via our what we currently know from IUPAC nomenclature, but it provides you a clear way of checking our relative assignments. So as we look, we have 3R stereocenter assignments and 1S stereocenter assignment, which matches our indicated assignments. We have 3R assignments and 1S assignment. So Marvin Sketch can provide you a way of at least checking how close your answer is to the ideal correct answer. And the more you know about nomenclature, the more effectively you can utilize Marvin Sketch to check your work. Does that make sense to everyone? So there's always a tool to check your work. But I'm showing you this kind of structure on the exam because it's a little harder to directly assess using Marvin Sketch. So it's a little more Google proof in a way. But nonetheless, it's a useful way to check your work. And there's no reason not to do that. Okay, so we've assigned, so stereocenters are carbons with 4 unique substituents that are present in, carbons with 4 unique substituents, yes. Of course, excluding meso cases. Yep. So in this next example, we're asked to draw the enantiomer. So all we do, so let's pretend we have our molecule. So all we do is we draw a mirror plane and we just reflect the molecule across the mirror plane. That's one method. And there's an even easier method than that. You draw the exact same skeleton. We draw the exact same molecule. I just flip every stereocenter. So anywhere you see a dash, you replace it with a wedge. Anywhere that you see a wedge, you replace it with a dash. And if you're feeling really adventurous, what you can do even is you can go back to this earlier example. And for example, here we said the center is R. I'm going to check this center right here. I'm just going to check really quickly. So priority 1, 2, 3. And we notice in our enantiomer, this center is S. So I've correctly drawn the enantiomer because my stereochemistry at each stereocenter is different. I always like to do that little check just to make sure I haven't made a mistake. You can be really thorough and you can check all the stereocenters, or you can check 1 or 2 and assume that you didn't make a mistake on the other 3 stereocenters in the molecule. Depends on how much time you have, but checking 1 stereocenter is just a good way of just making sure that everything adds up. So to draw an enantiomer, you draw your molecule and you flip every stereocenter, keeping the skeleton drawn in exactly the same manner. Does that make sense? Does that idea make sense to everyone?
Yeah.
Perfect. Okay, so now let's try to answer the question, how many total stereoisomers are possible? That's captured by the equation 2 to the n, where n is the number of stereocenters. And how many stereocenters do we have? 4, so 2 to the 4th, which would give us 2 times 2 times 2 times 2, which will give us 16. Now, how many other diastereoisomers? So how many diastereoisomers are possible? So to answer that question, we take our total of 16, we subtract our original molecule, and then we subtract our enantiomer, and that gives us 14 other diastereomers. Does that make sense? N is the stereocenters. Yes, exactly right. So to calculate the total stereoisomers, it's 2 to the n, which n is the number of stereocenters. If we wanted to know the diastereoisomers, we take our total minus our original molecule and then minus our enantiomer, because the enantiomer is not a diastereomer. And that tells us we have 14 molecules that have a different stereochemistry at one or more, but not all of our stereocenters. Does that make sense? In other words, it's 2n minus 2 for the diastereoisomers in most cases. That's, of course, assuming that there are no meso compounds. And since this compound's not symmetrical, there aren't any meso compounds to worry about. Does that make sense? Perfect, perfect. Any other questions on this example? Okay, so let's keep going now. Okay, this is where we're going to need our model kits. So for each pair of molecules, are they identical, enantiomers, diastereomers, constitutional isomers, or unrelated? Okay, so we're going to have to break out our model kit for this one. So let's try to put together these molecules using our model kit. Oops. So allow me a few moments, and you should be putting together your model kit as well for this molecule. And once we have our model kit put together, we can discuss. Okay. Okay, just making sure everything is normal. The camera flips whatever I put in front of it, so always have to be very careful when showing structures that everything is in order. Okay, now we have a methyl group, so the chlorine is in the plane of the page. Okay, we're almost there, And the methyl group is pointing out. So let me get that fixed. Okay. Okay, so here's our structure as drawn. Let's try to get it as close to the way that it's depicted. Okay, so we have our main chain, right? So we have our, oh, chlorine's on the wrong side. Okay, one moment. The camera likes to flip things around. Give me 1 second, just putting together the correct structure. I accidentally made the enantiomer because the camera flipped things. Okay, almost there. Okay, so just to check, here is our structure as made. Okay, we have our chlorine in the plane of the page. We have our methyl group. Does everyone see this methyl group pointing out towards us? Does everyone see how this methyl group has a wedge? And does everyone see the ethyl group pointing out towards us? Does everyone see that the ethyl group would be treated as having a wedge? So to correct that, as the ethyl group has a dash, let's flip this center. So now we have our ethyl group pointing away from us, our methyl group pointing out towards us, and now we're ready to begin working this structure. Okay? Does everyone get where we're starting from? Does this starting point make sense? Does everyone see how we put together this model? So we have our methyl pointing towards us. We have our methyl group pointing towards us. We have our ethyl group pointing away from us. Our chlorine is in the plane of the page. Now, from this point, what we're going to do is we're going to rotate our bonds. We're going to rotate our bonds so that the skeletons are drawn in the same manner, and then we're going to draw what we see. So I'm going to take this structure and drawing what I see after rotation, I have my same skeleton. I have my same skeleton. Okay, now where is our ethyl group? Where is this ethyl group? Is it pointing towards us or away from us?
Towards you.
So which one's closer to you, the hydrogen or the ethyl group?
Oh.
The hydrogen, right? So what do we assign the ethyl group, a dash or a wedge? What do we assign this ethyl group? We would assign the ethyl group a dash because it's pointing away from us. Perfect, perfect. Okay, now looking at our main chain, which group is pointing towards us? The hydrogen or the chlorine? What's pointing towards us? The hydrogen or the chlorine? The hydrogen. So we'll give the hydrogen a wedge and the chlorine a dash. Does everyone see how we rotated our bond? We just simply rotated this bond to get the same skeletal arrangement, and now we're comparing these two structures. Does that make sense to everyone, what's going on? Okay, so now let's look at this. Let's look and let's compare these two structures. Let's look and let's compare these two structures. So when comparing these two structures, our skeleton is set up the same, but, and this is really important, we do not end up with our substituents at the same position. So let's put our carbon numbers into place. Let's set up our carbon numbers. So we have 1, 2, 3, 4. Okay. So is the connectivity of these molecules the same? Is the connectivity of these molecules the same? Yes, it is. We have a chlorine at the 2 position, and we have an ethyl group at the 3 position. So we're going to have to keep going with this analysis. We're going to have to keep going with our analysis, and we're going to have to do a few more rotations. Okay, so based on that, let's keep going now, and let's try to rotate. Let's try to rotate our perspective for this molecule so it matches the perspective. Oops. Okay, so let's try to rotate this molecule so it matches the perspective that we have in our structure on the right. Okay, so let's set up our traditional view that we have so far. Let's set up our traditional view that we had so far. So here is our generic chain as matching our drawing. So now what we're going to do is we're going to rotate this molecule so that way this ethyl group is now on our carbon 2. So I'm going to rotate this molecule. So now my ethyl group is on carbon 2. Does everyone see how after rotation the ethyl group is now on carbon 2, on our carbon that's second from the right? So let's draw what we have now. So this time we have our chlorine pointing towards us, and we have our ethyl group pointing towards us, and our skeleton looks like this. Now what we're going to do, you don't have to necessarily show the rotations. I'm just showing them step by step so that way people who don't necessarily have a model kit can understand what we're doing. Perfect. So now what I'm going to do is I'm going to rotate my bonds so that my skeleton and my baseline skeletal arrangement is the same. So what I'm going to do is I'm going to rotate my skeleton, and I end up with this final skeleton after rotation, which looks something like this. So let's analyze this. Where do we see our chlorine? So is our chlorine pointing towards us or away from us? Is our chlorine pointing towards us or away from us? Away, yep, so we give it a dash. What about this ethyl group? Is it pointing towards us or away from us? It's almost hard to see it in the back, right? It's pointing away from us, exactly right. Perfect, perfect. So we've assigned our stereochemistries. Okay, so we've assigned our stereochemistries and we now have the following structure. Okay, so now that we have our following structure established, my question to you, if we compare our structures A and B, do they have the same stereochemistry at each center? Do they have the same stereochemistry at each center? Is the stereochemistry at each center the same or different? So comparing, do we see dashes and wedges at the identical spots in this molecule? So comparing A and B. They're different, right? And are they different and opposite at every stereocenter or only one stereocenter? Just one, right? And if they're different at one stereocenter, but not all, what do we call that? If they're different at one stereocenter or more, but not all, what do we call pairs of compounds with a difference in stereochemistry at one or more, but not all stereocenters? We call this pair a pair of diastereomers. Now, you may say, this method seems like an absolute pain. Is there a faster way? Yes. Remember, if you're really fast at assigning stereocenters, there's actually a trick. So I know, for example, that this center is S and the second center is S. Okay. So based on that, if I look at the stereochemistry of each of my centers in B, I notice the chlorine center is S. Makes sense. Same stereochemistry, same dash wedge notation for the same skeleton. While the opposite stereocenter is R. Does everyone see how only one stereocenter has a different configuration? Does everyone see how only one stereocenter has a different configuration? So then, these are diastereomers then. So that's the alternative method. You can manually assign each stereocenter and then compare and determine whether your stereochemical assignments are the same or different at all, one, or some of your stereocenters. You can apply the method from the original drawing, but keep in mind you will need to rotate your molecule in order to place the hydrogens in the back. So those are the two main methods. I find the rotate and match method is easier to visualize because you can literally take the model kits and shove them on top of each other and see whether they match or not. But the assignment method is also valid and can save you time if you're faster with it. Okay, yeah. So let's talk a little bit about that. So carbon 2, so to redraw this another way, to redraw A another way, we can also draw A like so. And this is via rotation. Okay, so chlorine's priority 1, the side group's priority 2, the methyl's priority 3. So then if we go from highest to lowest priority, that would be an S stereocenter. Does that make sense? Is that visible now? Yep, no problem. In this case, it's not quite rotation. You're just flipping your molecule 180 degrees. Yeah, essentially you are rotating the molecule overall. Yep. So there are two methods to determine enantiomers, diastereomers, or unrelated compounds. Okay, let's look at this next example. And this one is a little bit interesting to keep in mind. This one's a little bit interesting, and you're going to need to be really careful with these examples. Okay, so we're going to start and we're going to convert each of our structures into dash wedge notation. Now this is a Newman projection, so that means we're going to have to break out our cameras and break out our model kits. And I'll start off by showing what this would look like from a sawhorse perspective. And there's a fast trick to draw out the bond line structures. So all you do is you take your molecule and you circle the two substituents that are separated by 180 degrees. Does everyone see these two anti-substituents? Okay, so these are gonna be the principal parts of our skeleton. Okay, now once you have that established, now that you have that set up, we're gonna look and we're gonna see what happens in our model kit as we rotate this structure, okay? So just like before, we have our ethyl group pointing up top. We have our methyl group on the right. Okay, so here's our first step. Here's the first half of this molecule. We have our ethyl group up top, our bromine on the left, and our methyl group on the right. Now let's keep going. Now let's keep going and keep putting together the pieces. So now let's deal with the back carbon. Let's deal with the back carbon. We have a hydrogen on the left, a methyl group on the right. So let's put in that methyl group. And then pointing down, we have an alcohol. Okay, here we go. So here's our complete Newman projection structure. So let's zoom out and let's take a look. So in the front, we have our halogen, our bromine on the left, methyl on the right, ethyl up top. Now looking in the back, what do we see in the back? So we have our alcohol pointing down, our our back methyl, hard to see. See this back methyl right here, all the way back here? Back methyl on the left, hydrogen on the right. Okay, so now that we have our Newman projection set up, okay, can everyone see how this matches our Newman projection? Does everyone see how this matches our Newman projection? Okay, so the trick that I use is I take with my hands and I'm gonna grab my two methyls, okay? And now all you have to do is just turn your molecule on its side. Okay, now it's really important that when we draw out our chain, you draw the chain exactly as you see it. So we have this zigzag chain, okay? And now, as we see, this ethyl group, is it pointing towards us or away from us? This ethyl group, is it pointing towards us or away from us? This giant ethyl group, where is it pointing? Towards or away? Towards us, yep. So we're gonna draw the ethyl group with a wedge. What about the bromine? What about the bromine? It's so hard to see because it's in the, is it front or in the back? It's away from us, yeah. Okay. So this is known a bit, I don't know if it has a name. I like to call it the dividing line method. And the reason why I call it that is because anything on this right-hand side will get a wedge. Anything on the left-hand side will get a dash. So let's see how this holds up. Looking at our hydrogen, what do we assign our hydrogen? Is our hydrogen pointing towards or away from us? It's towards, so it gets a wedge. And our alcohol, is it pointing towards or away from us? Away, exactly right. Okay, perfect. So now that we have that all set up, so the dividing line method's a pretty fast shortcut. Now, before I apply that method to this structure so this is structure A. Now, before I apply that method to structure B, I'm gonna do a little rotation. So I'm gonna rotate this molecule and we're gonna build from the following Newman projection. The reason why I'm doing that is I want my methyls in the same spot. I like to make things as easy as possible for myself. And once I have that set up, once I have my methyls in the same spot, I can begin this dividing line method. So just drawing my dividing line, circling my two methyls. Oh, one moment. One moment. Okay, so continuing on from where we left off, Okay, so circling our two methyls, drawing our dividing line, we're going to draw out our skeleton. Okay, so as we see, if we draw out our baseline skeleton, we'd assign a wedge to our bromine and a dash to our ethyl group. And we'd assign a wedge to our alcohol and our dash to our hydrogen. To help everyone justify that conclusion, to help everyone notice that conclusion and more effectively understand what's going on, let's showcase our analysis of this model, and let's make a model of structure B just to justify that conclusion. Okay, so here is our model. Here is our model of structure B. We have our bromine on the right, our methyl on the left, our ethyl up top. We have our alcohol on the right. We have our methyl on the left and our hydrogen in the back. Is everyone able to visualize this Newman projection? Does everyone see how this Newman projection matches what we've seen in our drawing? Does everyone have this same model kit made up? Can I get some feedback in the chat to make sure everyone's following along? Okay, so now what we're gonna do, just for consistency's sake, is we're gonna rotate this structure, gonna rotate this Newman projection. So that way the methyls are on opposite sides. Just for consistency, so that way we always have our methyls on the same side and our chain looks the same. Okay, so now that we have both our methyls, what we're gonna do is we're just gonna turn our chain on its side and then draw what we see. Let's turn it the other way. Let's turn it the other way just to avoid any issues with that and to make sure our atoms end up on the same side. Okay, there we go. Okay, so drawing our chain in the same manner, where is our bromine pointing? Is our bromine pointing towards us or away from us? Where is this pointing? Towards, right? And where is our alcohol pointing? Towards, right? So both our bromine and our alcohol get a wedge. So if we compare structures A and B, are the stereocenters opposite at each stereocenter? Is the stereochemistry opposite at each stereocenter? What do we call structures that have the opposite stereochemistry at each center? What do we call those? Enantiomers. So this pair would be a series of enantiomers. Does that make sense to everyone? Perfect. So the dividing line method's pretty useful for Newman projections, and we've provided a justification by actually working through and analyzing a Newman projection with our model kit. Okay, let's look at this third pair. This one's a little tricky. So what does everyone think? At first glance, does anyone notice anything odd here? what do we call a series of structures? So does anyone notice anything odd, anything a little disconcerting here with this structure? There's something that I always want students to look out for in structures. Why am I strongly hinting about something? What's a problem with this second set of structures? Why do you think it's a trap? What's suspicious about this structure? What's suspicious about it? The stereocenters are all opposite, yeah. So we think it's an enantiomer, but what's the problem? What's the problem? The word starts with S. This molecule would be considered. Is it symmetrical? Is this, yeah, it's symmetrical. Now, as we notice, if we draw this axis of symmetry or plane of symmetry, are both substituents identical in stereochemistry across our plane of symmetry or axis of symmetry? It's identical. So these two structures are considered meso and they're identical. Now, this is really easy to see if you make a model kit. And I find a lot of at least in my opinion, a lot of the difficulty in organic chemistry just simply stems from developing this three-dimensional reasoning, just being able to visualize a structure and see that, in fact, a set of structures are identical after rotation. Okay, so this is why I encourage you always to make a model kit. You have almost unlimited time in your exam taking week, so really utilize that time. Okay, so let's turn on the camera. And, oh, whoops, wrong stereochemistry. Okay, so as we notice, does everyone see how the methyl's in the front and the oxygens are in the back? Okay, so I've made structure B. Okay, now without rearranging my bonds, I am literally just going to rotate this molecule. Ready? I'm going to rotate this molecule on its axis of symmetry. So I've rotated this molecule. Now what do we see? Where are our oxygens? Where are the oxygens? Towards us. And where's the methyl group? So are these two structures identical if all I'm doing is rotating them? Yes, so that's what we mean by a meso compound. It's compounds with an axis of symmetry that as a result are identical after rotation. Does that make sense? You can note that this compound's meso, yeah. Does this example make sense? Okay, let's look at this last example. Cyclohexane stereochemistry. Okay, the fastest way to do this is just to convert these structures into dash wedge notation. So is this chloride pointing up or down? Up, yep. Is the methyl pointing up or down? Down, yep. Okay, in the structure on the right. Is the chloride pointing up or down? It's pointing down. Is the methyl pointing up or down? Up, yep. I mean, you can even draw this, oh, it gets a little tricky after a ring flip. So this structure would look something like this. So comparing these two structures, do we notice the stereochemistry is the same or opposite at each of our stereocenters? Opposite. So what will we call that then? What will we call this pair of compounds? Enantiomers, exactly right. Does that make sense to everyone? Perfect, perfect. Let's keep going now. And in this case, for each of these pairs of molecules, we're asked to draw the two chair conformations, and we're asked to draw the Newman projection for each chair conformation of A and B, sighting along the C2, C3, and C5, C6 bonds. Okay, so let's get started with that then. So I'm going to, as I'm citing, I'm going to arbitrarily designate and start with, in my chair conformation, I'm just going to arbitrarily start as this at carbon 1. It's completely arbitrary, but it's my starting point. Okay, so at carbon 1, I have two methyls, one up, one down. Okay, carbon 2 doesn't have anything. Carbon 3 has a chloride that's pointing up. The wedge tells us it's pointing up. You can also use the axial equatorial method, but I just like to use up down, it's easier. Okay, so we draw out our chloride and our hydrogen. Carbon 5 has a methyl group that's pointing up and a hydrogen that's pointing down. Okay. Okay, so in the problem, we're asked to draw out the Newman projections. We're asked to draw out the Newman projections looking down the C2, C3, and C5, C6 bonds. Okay, so we're going to look down the C2, C3, and C5, C6 bonds. So this carbon right here is carbon 4. Does that make sense to everyone where we're looking? Does that make sense to everyone where we're looking? Does that view make sense?
Yes.
And just to help us visualize it, again, not to sound like a broken record, but let's make a model of this because it's really important to be able to translate your cyclic structures into Newman-like projections. Okay, 1, 2, 3, 4, 5, 6. almost there. So we have our cyclic system. Okay, we have 2 methyl groups at carbon 1. And I really encourage you, especially for these problems, it's easy to make a model kit. It doesn't cost you anything, and it will save you a lot of grief when you're working through these examples on paper. I find we're more capable of visualizing structures that we can see in 3-dimensional space rather than just on pen and paper. But of course, whatever you're comfortable with, that's more than okay with me, as long as it's accurate. Okay, so let's take a look at this model. So let's take a look. So at carbon 1, we have our, so at carbon 1, we have our 2 methyl groups. So at carbon 3, we have our chloride. And at carbon 5, we have our methyl group. So now what we're going to do is we're going to look down. And what we're doing is we're looking down. In this case, they want us to look down the carbon 2 and carbon 3. Okay, and the carbon 5 and carbon 6 bond. Okay, so that gives us something that looks like this. Okay, so looking down our bonds, we see that we have our chloride pointing up, our hydrogen pointing adjacent. Does everyone notice how carbon 4, which is our bridging carbon, is pointing down? Does everyone see that? How the bridging carbon 4 is pointing down? Okay, now as we notice also, we have a methyl group pointing up top, and we have a hydrogen pointing to the left. Now let's fill out our remaining positions. So in the back on carbon 6, we just have our 2 hydrogens. Okay, in the back of carbon 3 on carbon 2, we have our 2 hydrogens. And on carbon 1, we have both of our methyl groups. And as we can tell immediately, they're just bumping into everything. Okay, so we've completed drawing our Newman projection. Now let's do a ring flip. So carbon 1 goes down, carbon 4 goes up. So at carbon 1, we still have our 2 methyl groups. So this is carbon 1 now. At carbon 2, we don't have anything. At carbon 3, our chloride is still pointing up, but instead of being axial, it's equatorial. Carbon 4, we still have our hydrogens. And then carbon 5, our methyl group is still pointing up, but this time it is equatorial. Okay, so now looking down the same bond, so looking down the carbon 2 and carbon 3 bond and the carbon 5 and carbon 6 bond, we see carbon 4 is right here. So our chloride this time is equatorial. We have our 2 hydrogens. The methyl group is equatorial. And carbon 1, we still have these 2 methyl groups as always. Okay, does that set of Newman projections make sense to everyone? It's for your own benefit. It's for your own benefit. The axial and equatorial positions are implied by how you draw your Newman projection, but it's important to be meticulous about axial versus equatorial, because it can lead to pretty large variations in your final response. Okay, so personally, there's no reason to not utilize the structure A to help draw structure B. Our only difference is this stereocenter, right? Our only difference is the chloride, right? Does everyone see how the only difference is our chloride? So then, as a result, we can essentially draw the exact same structure as structure A and just change the chloride, right? So I'm just copying and pasting structure A, except I change the chloride, and don't forget that last part. Okay. Okay, so the only thing that's different in these 2 structures is our chloride. Everything else is the same. So it really is just copying and pasting and flipping the center for the chloride. But again, don't forget to flip the chloride stereocenter or it won't be very good. Okay, so now we have this set up. We have both of our Newman projections. Okay, now we're ready to do some energetic analysis. Okay, so we're asked to calculate the energy associated with steric and torsional strain for each chair conformation and circle the lowest energy chair conformation. You're going to want to do this on a separate piece of paper on the actual exam, but I'll do this on the side so that way it's all in one place. So looking at the structure, we'll start with structure B1, and I'll call it. So B1, in terms of our diaxial interactions, we have a methyl-methyl, and we have a methyl hydrogen. Any other diaxial interactions that we need to note? So what's the energy penalty for a methyl-methyl diaxial interaction? Methyl-methyl. Does someone have that value? So what is a methyl-methyl diaxial interaction? What's the energetic penalty for a 1,3 diaxial interaction between 2 methyl groups? Does anyone have that value offhand?
Is it 11?
Yep, exactly.
Kilojoules
Right.
per mole?
Yep, exactly right. Roughly 11 kilojoules. Perfect, perfect. So it's important that you're familiar with the methyl-methyl diaxial interactions, just so that way you can appropriately estimate the amount of strain present in our ring system. Does that make sense to everyone?
Yeah.
Okay, perfect, perfect. So we also have a methyl hydrogen diaxial interaction. What's the approximate energy of a methyl hydrogen diaxial interaction? And this one you
6.0 kilojoules.
that would be an eclipsing interaction. What about a diaxial interaction?
Oh, hold on.
What is the diaxial interaction roughly? What is our estimation? It's roughly 3.8 kilojoules. Does that make sense to everyone? Does that number make sense? You should be familiar with these diaxial interaction energy values, and you should be familiar with the common eclipsing, gauche, and other interactions. These are tabulated in the chapter 4 and chapter 5 notes.
For the gauche and eclipse, that's on page 28 of
Yes. And
chapter 3
that
notes.
refers to in Newman projections when your substituents are eclipsed or gauche. The gauche methyl interaction also pops up when discussing a methyl hydrogen diaxial interaction. That's why often a methyl hydrogen diaxial interaction is known as a gauche interaction. Does that make sense? And then chapter 5 has the A values and strain associated with different diaxial interactions. Does that clarify where to find the data that you'd need? And then just to clarify, a methyl-methyl is a little bit greater than 12. It's closer to around 15 kilojoules. Very similar in energy to a methyl-methyl. Eclipsing interaction. Okay, so now that we have our estimates established, we calculated our total amount of strain to be roughly 18.8 kilojoules. Okay, the next thing we have to look at is in structure B2, what interactions do we have? What interactions do we have? So in this case, as we notice, we have a methyl chlorine 1,3 diaxial interaction. We have a methyl hydrogen 1,3 interaction and a chlorine hydrogen 1,3 interaction. So I would consider chlorine, so if we compare the A values for chlorine and a methyl group, chlorine has about half of the A value. And as a result, the amount of diaxial strain that a chlorine imparts is roughly half of a methyl group. So a chlorine hydrogen interaction is about 2 kilojoules. A methyl hydrogen is still 3.8 kilojoules. And a methyl chlorine, would someone like to give a ballpark? What would be the rough amount of penalty for a methyl chlorine interaction if chlorine can be thought of very similar to a hydrogen, but a little bit more bulky? What would the approximate value be? just ballpark. Would you expect it to be around 15, way less than 15, around 4, a little bit more than 4? What would a ballpark estimate be if a chlorine is about, it exerts about half the amount of strain as a hydrogen? Yeah, sure. So if we go to chapter 5, oh, sorry, not chapter 5, that would be chapter 4 for that. There we go. So if we go to chapter 4, we had a detailed discussion of A values, which indicate the amount of strain imparted by different substituents. So as we notice, the A values for a 1,3 diaxial strain, notice that chlorine has about half of the strain value as a methyl, or almost a fourth of the strain value as a methyl group. So a chlorine hydrogen interaction, looking at our table on page 22, that the methyl hydrogen interaction is 3.8. The chlorine hydrogen is about 1 kilojoule. So what would you expect a methyl chlorine interaction to be? Would you expect it to be close to a methyl hydrogen interaction? Larger, smaller? If chlorine has about the same amount of A value strain as a hydrogen atom, if not a little bit more. What would we estimate a methyl chlorine 1,3 diaxial interaction to be around? Yeah, I'd say around 4 to 5, closer to 5 since it's a little bit bulkier, but 4 would be a reasonable proposal. Okay, so adding it up, we have 9.8 kilojoules. If I wanted a very exact strain calculation, I'd give you the diaxial strain, but most of these you should have memorized, like a methyl hydrogen, chlorine hydrogen, and methyl hydrogen. Those are all tabulated and ones you should be very familiar with. Okay, what we can conclude overall from this, discussion, which is the lowest energy chair conformation, B1 or B2? Which chair conformation is lower in energy for this specific molecule? Which one has the least diaxial strain, B1 or B2? Just comparing the numbers. B2, yep, so we'll circle B2. Okay, does that analysis make sense? We tally up all of our 1,3 diaxial interactions and Gauss interactions. We add up the total strain associated with those interactions, and whichever species has the least amount of diaxial, steric, and torsional strain, we identify as the lowest energy chair conformation. Does that make sense? Okay, so now that we have that established, let's look at A now. Whoops. Okay, let's look at each of our structures for molecule A. So let's look at A1. Okay, so in this case, I see a methyl-methyl. I see a methyl chlorine. And I see 2 of them. So adding up, we know a methyl-methyl interaction is around 15 kilojoules. A methyl chlorine is around 5 kilojoules, and we have 2 of them. So in total for A1, we'd have 25 kilojoules of strain. Does that calculation make sense? Does that follow our logic that we've used previously? Okay, Perfect. Now let's look at this next ring flipped form. So in this case, we have a methyl hydrogen interaction, and we have two of them. So that is 3.8 kilojoules times 2. And that in turn gives us 7.6 kilojoules. So which conformation is the absolute lowest in energy? Which conformation is the absolute lowest in energy? A1 or A2? Which one's lower in energy? A1 or A2? A2. Now, if we add up all of our strain, which structure, A or B, which molecule is lower in energy, A or B? Which molecule has the lowest energy conformation, and overall, which molecule is lowest in energy? A or B, just comparing these energy values. Which molecule is lowest in energy? Wait, A or B, which one's smaller, 9.8 or 7.6? Wait, which one's smaller, 9.8 or 7.6? So then the lower energy molecule would be A. Does that idea make sense to everyone? In general, the lowest energy molecule will have the conformation with the least amount of axial substituents. Does everyone see why A is lower in energy? Just looking at the energy values for each of our conformations.
Yes.
Perfect. Any questions on this example?
Where is the second methylchloral interaction in compound A?
In compound A, the A1. Yes. Okay. So as we have two methyls, there would be two methylchlorine interactions.
Oh, okay.
Does that make sense?
Yeah, I was looking at the Newman and not the other projection.
I mean, you can see that from the Newman as well, right here. But it's often easier looking at the chair conformation as the substituents are drawn axial, and you can even see them physically close together in 3D space.
Yeah, it's much easier to see it that way.
Mm-hmm. The Newman projection is useful because we'll use the Newman projections for analysis for elimination reactions. So I want to make sure that skill is developed. Does this example make sense? Perfect. So let's keep going now. We're asked to draw the structure for 2-methylpentane. Okay, now this is the part where you really want to make sure you have your nomenclature down, just so that way you don't accidentally draw the wrong structure. Okay, so here's 2-methylpentane. Deliberately chosen so there's no chiral centers. Okay, so there's 2-methylpentane. And I'd like you to draw the Newman projections for each of the conformations of 2-methylpentane, looking down the C2-C3 bond. Okay. So looking down the C2-C3 bond, we have our 2 methyl groups. Okay, so drawing out our Newman projection, looking down the C2-C3 bond, I'm going to draw one of my methyl groups pointing up, and then I'm going to draw the back chain, which has 3 carbons pointing down. Okay, perfect. So this will be our first conformation. We'll call this the 0-degree conformation. And we see in this case our substituents are anti. Okay, I'm going to continue to rotate, and I'm just going to rotate the back carbon, and I'm going to draw each of the Newman projections after rotation. So I rotate my back carbon. Okay, that'll be our 60-degree structure. Let me draw these a little bit closer so that way we have enough space. Is everyone comfortable with how I've drawn out these initial Newman projections? Does this make sense to everyone so far?
Yeah.
Don't be shy to stop me with a question, as this review is really for you. So if you have any questions, it would be good to ask. Oops. That should be in the back. You keep the front substituents in the same position and you just rotate your back substituents. Oh, I missed one. I'm skipping some steps here. So we have 60, 120 is the directly aligned conformation. Okay. Oh. Oh, I see. I skipped a step. Sorry about that. The 60 degrees, if we rotate 60 degrees, now our substituents should be completely eclipsed. There we go. Now for 120. Okay. For 100. Okay, so we're just continuing to rotate. You can write ME, but it's not preferred. CH3 would be better, just to note it. Okay, so we're continuing rotating our back carbon, and we're drawing out the Newman projection after each rotation. Okay, so now that we have this set up, now that we have our angles set up, and now that we've drawn out each of our Newman projections, we're going to calculate the energy of each conformation and draw a graph of energy versus dihedral angle. Okay. So with that established, what we're going to do is we're going to correct our labels to be more reflective. I always like to start by drawing the anti-configuration as it makes it easier on me. We have 180, 240, 300, 0, 60, 120, so to showcase our rotation from our starting point, so let's look and let's find our most eclipsed conformation. That would be here. So this is our eclipsed conformation. This would be our 0, 60, 120, 180, 240, 300, and 0. So in this case, we have a few anti-conformations in this list. Okay, so now let's calculate the energy of each of our conformations. So in this case, looking at our interactions, in this case, we have a methyl-propyl Gauss interaction. And given that a methyl-methyl Gauss interaction is about 3.8 kilojoules, and a propyl group is a little more bulky, what would we estimate? The reason why we relabeled the angles is because when we make our plot, we're looking at the dihedral angle between our bulkiest substituents. I always like to start drawing the anti-conformation first because it makes it easier for me to visualize what's going on. And the anti-conformation and the eclipse conformation are often most important for our Newman projection plots. But to be entirely correct, you have to start with 0 degrees between your bulkiest substituents. So for a methyl-propyl Gauss interaction, what would we estimate a methyl-propyl Gauss interaction to be, roughly? If a methyl-methyl is around 3.8, would a methyl-propyl be greater or smaller? Would we expect a methyl-propyl Gauss interaction to be larger or smaller than 3.8? Larger, exactly right. So I'd estimate it to be around 6 to 7 kilojoules, roughly. So that's the only interaction we have so far. In this next structure for 240 degrees, we have a methyl hydrogen eclipsing interaction and a propyl hydrogen eclipse. So we have 2 methyl hydrogen eclipsing and a propyl hydrogen eclipsing. What is the energy of a methyl hydrogen eclipsing interaction? What is the energy of a methyl hydrogen eclipsing interaction? So a methyl hydrogen eclipsing interaction is, yes, 6 kilojoules. Yep. And we have 2 of them. So we have 6 kilojoules times 2. Okay, perfect. Would we estimate a propyl hydrogen interaction to be greater or smaller? Would we expect a propyl hydrogen interaction to be larger or smaller? So it says, based on the logic that a propyl group is larger, what would we estimate a propyl hydrogen eclipsing interaction to be around? Would we expect it to be greater or less than 6 kilojoules, just based on steric size, steric bulk? What do we think? So we've established previously like a propyl group is bulkier, right? It would be greater. So I'd estimate it to be around 7 to 8. Let's just go with conservatively 7 kilojoules. So that gives us 19 kilojoules of total torsional strain. Okay. Let's look at our next anti-conformation. In this case, we have a methyl-propyl gauche interaction, which we already established was around 6 to 7 kilojoules, right? Looking at our 120-degree structure, we have a methyl hydrogen, a hydrogen-hydrogen, and a propyl-methyl eclipsing interaction. So let's tally it up. What would we estimate a methyl hydrogen eclipsing interaction? We've already established that to be 6 kilojoules. What about a hydrogen-hydrogen eclipsing interaction? What's a hydrogen-hydrogen eclipsing interaction? What's the tabulated value for a hydrogen-hydrogen eclipsing? 4 kilojoules. Okay. Now for a propyl-methyl eclipsing, we know that a methyl-methyl eclipsing interaction, if we punch it and we look for our table, so looking at our methyl-methyl eclipsing interactions, so we know from our table that a methyl hydrogen eclipsing interaction is 6, a hydrogen-hydrogen is 4, and that a methyl-methyl eclipsing interaction, looking at our table, is around 11 kilojoules. So what would we estimate a propyl-methyl interaction to be? What would a propyl-methyl eclipsing interaction be? Would it be greater than or less than 11? Would it be greater than or less than 11? Greater, yep. I'd estimate it to be around 13, yep. So we add this up and we get 23 kilojoules of strain. For our 60 degree, we have 2 propyl methyl gauche interactions, which we would estimate to be 2 times around 6, which gives us 12 kilojoules. And for our final eclipsed interaction, we have a propyl methyl, a hydrogen hydrogen, and a methyl hydrogen eclipsing interactions. And in turn, so in this eclipsed conformation, that would give us a total energy of 13 plus 4 plus 6, which gives us 23 kilojoules. Okay, so then in terms of our highest energy conformation, we're going to put a box around each of our eclipsed conformations. And then for our lowest energy conformations, we're going to circle our 2 anti-conformations. Does this make sense to everyone? Does everyone see how we calculated the energy values and we identified the lowest and highest energy conformation?
Yes.
Perfect. So now what we're going to do is, oh, that's about it. We don't even have to make a graph this time. So in general, if you're aiming to determine the highest and lowest energy conformation, so the 0 degree Newman projection, the 0 degrees, the degrees refer to the separation between our substituents. And the 0 degrees typically refers to 0 degree dihedral angle between the two bulkiest substituents. Does that answer that question? Perfect. So in general, the highest energy conformation will have your bulkiest substituents eclipsed. The lowest energy conformation will have your bulkiest substituents anti to each other. Okay, so let's look at the next example in this exam. And in this case, we're asked to indicate the stereochemistry at each chiral center and draw each molecule in dash wedge notation. Okay, so first things first, we're dealing with a Fischer projection. Okay, so let's convert the Fischer projection into a dash wedge projection. So we have our bromine and back, both the hydrogen and our hydroxyl group are pointing out towards us. We have our hydrogen and chlorine pointing out. And we have our carboxylic acid pointing away from us. Okay, so again, we're going to make a model of our structure. So again, we're going to make a model of our structure. So let's put together a model for this Fischer projection. And then from there, we can analyze this model to determine the stereochemistry at each carbon. So let's put together a model kit and then we'll share our screen once we have that set up. Okay, so here's a model of the following structure. So as we notice in our Newman projection, our alcohol and hydrogen are pointing towards us. Same with our chlorine and hydrogen. Now, what we're going to do in this Newman projection, and all we're going to do to convert this Newman projection into a normal dash wedge structure is we're just going to turn it on its side and draw what we see. So in this case, we have our following setup. Okay, and now my question to you, is this chlorine pointing out of the page or into the page? Out. Yep, so we're going to draw the chlorine with a wedge, the hydrogen with a dash, and the alcohol as well is pointing out of the page. So now that we have that set up, we've drawn this structure in dash wedge notation. Now all we have to do is assign our stereochemistry at each center. Okay, so chlorine's priority 1. If we look at our adjacent carbon, we have 3 oxygens and a hydrogen attached versus an oxygen, 2 carbons, and a hydrogen. So this group is priority 2. This group is priority 3. Tracing, this first center would be R. For our second stereocenter, oxygen's priority 1. So we have a carbon attached to a bromine versus a carbon attached to a chlorine. Bromine is priority 2 because it has the next highest molar mass, while the carbon attached to the chlorine is priority 3. So tracing from highest to lowest priority, that gives us a configuration of S. Does that make sense to everyone? So yes, so looking at the second carbon, bromine is a higher atomic mass than chlorine. So the carbon with the bromine attached is higher priority. Does that make sense? Perfect. So we've assigned the stereochemistry and we've drawn out this structure in dash wedge notation. Does that make sense to everyone so far? Any questions so far? Okay, let's look at this next example. So in this case, we are given a cyclic structure. So drawing out our ring. Now, looking at this alcohol, is this alcohol pointing up or down? Do I give it a dash or a wedge? Down, so it gets a dash. Okay, looking at the bromine, is it pointing up or down? Up, so it gets a wedge. And is this methyl group pointing up or down? Up, so it also gets a wedge. Okay, so just drawing this structure one more time, so that way we have more space to assign stereochemistry. Okay, so let's assign priority now. So bromine's priority 1. If we look one carbon over, we have sulfur, carbon, carbon, and hydrogen versus carbon, carbon, and 2 hydrogens. Sulfur wins out. So this group's priority 2, this group's priority 3. Tracing, we have a clockwise rotation. So that in turn gives us an R stereocenter. Now for the methyl stereocenter, we have sulfur, which is priority 1, a carbon attached to the bromine, which is priority 2, and a carbon that just has hydrogens, that's priority 3. Tracing. One moment, allow me to reload OneNote. Oh, never mind. Yeah, I need to reload OneNote. Okay, so just to recap our priority assignments, sulfur's priority 1, the carbon with the bromine's priority 2, the methyl's priority 3. Tracing from highest to lowest priority, we're going counterclockwise, so this center will be S. Okay, now to handle the alcohol stereocenter. To handle the alcohol stereocenter, all we're going to do is we're going to rotate our molecule 180 degrees, and that gives us the following tentative structure. Okay, so now that we have that set up with our hydrogen in the back, our alcohol's priority 1. Looking 1 carbon over, this carbon is attached to 2 carbons and 2 hydrogens versus a sulfur, a carbon and 2 hydrogens. Sulfur wins in priority. And tracing from highest to lowest priority, we're going clockwise. So the third center would be R. Does that make sense to everyone? Perfect. Okay, we're now dealing with a Newman projection, but remember we have a pretty fast method of the dividing line method. So we circle our 2 methyl groups. They're going to be the core of our skeleton. And anything to the right of the line gets a wedge. Anything to the left of the line gets a dash. Okay, so that means our ethyl group gets a wedge, while this carboxylic acid gets a dash. Okay. That also means that this ether gets a wedge, while the alcohol gets a dash. Now, because our highest priority group is not in the back in either case, we're going to have to do some rotation. So let's break out a model kit and let's discuss this structure. So we're putting together a model for this structure. So let's keep going with that. And then we'll be able to rotate the model to place our lowest priority groups in the back. Okay, so here is our Newman projection. Oops, one moment. There we go. So here is our Newman projection. So as we see, we have our ethyl group up top, our methyl group in the front on the right, our carboxylic acid in the front, our carboxylic acid in the front on the left. We have our alcohol pointing down. We have our ether, it's a little hard to see. We have our ether on the right, and we have our methyl group on the left. Okay, so now that we have that set up, now that we have that all set up, all we did for rotation is we placed our hands on each of our methyl groups and we rotated our molecule. So here's our current view of our molecule that we have drawn out. Okay, so now what we're going to do in this case is we're going to rotate our bonds so the lowest priority group is in the back. So we want this methyl group, which is our lowest priority in both of these structures. We want our methyl group, which is our lowest priority, to be in the back. So I'm going to rotate this structure so that my methyl group is in the back, and then I'm going to draw what I see. Okay, now I'm not done just yet because I'm going to rotate my other methyl group so that the methyl group is in the back. So in both cases, we see that our methyl groups are now in the back. Our methyl groups are now in the back. Does everyone see how our methyl groups are in the back? We can't see them anymore. Okay, so now we're going to draw out our chain. So in this case, our carboxylic acid is now in the front, and our ethyl group is in the back. Our alcohol is in the front. Our ether, oh, sorry. Our methyl group is in the back, sorry. Our ether is within the plane of the page, and our methyl group is in the back. Okay, perfect. So now we're ready to analyze this structure. Okay, so looking at this in terms of priority, the carboxylic acid is priority 1. The second group is priority 2. The ethyl is priority 3. Tracing, that gives us an R stereochemistry. For our second stereocenter, the ether is priority 1. The alcohol is priority 2, and the carboxylic acid is priority 3. So tracing, that gives us an R stereochemistry. Does that make sense to everyone? Okay, so then let's keep going now.
So Professor, before you move on, can you scroll up just a little bit? I missed something on the first, the very top one. Oh, okay, never mind. Thank you.
Yes, and you're more than welcome to color code as long as your scan file is in color. Make sure the scanner scans in color if you use color coding. Okay, we're next asked to draw the lowest and highest energy conformations for the following molecule. Okay, well, by definition, one conformation will be the lowest and one conformation will be the highest. Let me rephrase this. This is referring to the chair conformations, just to avoid people drawing boat conformations or half chair. Yeah, they can. The notes take a while to process into a PDF. Okay, so assigning this as carbon 1. So is this tert-butyl group pointing up or down? It's pointing down, right? So we're going to draw our tert-butyl group, equatorial, pointing down. Okay, is this ethyl group pointing up or down? Up, so we're going to draw it as equatorial up. And this alcohol, is it pointing up or down? Down, so it'd be equatorial down. Okay, we're then going to draw the ring flip. So carbon 1 goes down, carbon 4 goes up. And in this case, on carbon 1, our T-butyl group is now axial. Our ethyl group is now axial. And our alcohol is now axial. So which of these conformations is going to be the lowest in energy? Which of these conformations is going to be the lowest in energy? The equatorial conformation or the axial conformation? Equatorial, exactly right. So this conformation, which has all equatorial substituents, will be the lowest energy conformation, while the conformation, the chair conformation, I should say, with all axial substituents will be the highest energy conformation. Does that idea make sense to everyone?
Yes.
Perfect. Perfect, perfect. Okay, so let's look at the following case where we're asked to draw some Newman projections, and we're asked to draw the lowest and highest energy conformations looking down C2, C3. So drawing out our draft Newman projection, we have our ethyl group, a methyl group, and a hydrogen, and then an ethyl group, a methyl group, and a hydrogen in the back. So this conformation that I've drawn is the eclipsed conformation where our largest substituents are eclipsed. This would be our highest energy conformations because we have an eclipsing interaction between all of our largest substituents. So this all eclipsed conformation with our bulkiest substituents is the highest in energy. Does that make sense to everyone? Does that idea make sense? Perfect. Now, the lowest energy conformation has the greatest amount of separation, the greatest dihedral angle between our bulky substituents in general. So our anti-conformation would be the lowest in energy. And our anti-conformation would look something like this. Does anyone think of another lower energy conformation that we could draw? Is there another lower energy conformation that we could draw? Other possibilities would include the following. Or something like this. So analyzing each of these possible conformations, in this first case, we have an ethyl-ethyl and a methyl-methyl Gauss interaction. In the second case, we have an ethyl-methyl times 2 and a methyl-methyl. So this one's going to be higher in energy. In this case, we have an ethyl-methyl times 2, and we have a methyl-methyl Gauss interaction. So which of these structures, which of these proposed conformations has the least amount of torsional and steric interactions? So looking at these three possible anti-conformations, which of these conformations is lowest in energy? So let's title them A, B, and C. Which one's lowest in energy? A, B, or C? What does everyone think?
Wouldn't it be C because the ethyl and methyl group are the farthest away, or?
That is generally the case. But if we take a tally of our interactions, which structure has the least amount of Gauss interactions? And we see that A has the least number of Gauss interactions. So A would be the lowest in energy. Now, the point of this process is to show that the shortcut generally works, but it's important that you go through and just check all of your staggered conformations to make sure there's not a potentially lower energy conformation hiding in the set. Does that make sense? So generally, we would have expected C to be the lowest energy, but upon closer inspection, when we drew out all of the potential conformations, we noticed that it actually A is lowest in energy. Oh, whoops, sorry, this should be ethyl, ethyl, ethyl. There we go. So we have a methyl-methyl and ethyl-ethyl Gauss interaction, but we have less total Gauss interactions in structure A. Does that argument make sense to everyone? Does that clear things up?
Yeah.
So when in doubt, draw everything out just to double check. Okay, let's focus on naming these compounds. Notice these compounds have stereocenters, so we're going to have to account for the stereochemistry. So I'm going to draw this compound and its this compound's a little funny. Does anyone notice why I'm somewhat laughing at this compound? Does anyone notice something a little special about this compound? Anyone notice something funny? Do these stereocenters actually mean anything in this case? Do the stereocenters mean anything in this case? No, this compound's symmetrical. It's meso. Yep. So always double check before you decide if you have to do extra work. So then, looking at our carbon numbering, we can either number 1, 2, 3, 4, or number 1, 2, 3, 4. So we're comparing a methyl group to a T-butyl group. Do we care about the T for alphabetical? What do we care about, the T or the B in tert-butyl? The B, yep. So the tert-butyl gets priority. So we name this as 1 T-butyl, 1 T-butyl, 4 methyl. And since this is a 6-membered ring, we'd call this cyclohexane. Does that make sense to everyone? So the stereochemistry doesn't matter in this case. And that sometimes confuses computers. So sometimes computers will say this has the stereocenter when us humans know it does not. It's symmetrical. Okay, let's look at this second example. So in this case, we have to find the longest chain. So 1, 2, 3, I find the longest path, so I go down this path. And then if we have a choice between 2 chains, we pick the most branched path. So we'll go down this top path. Our other option is to count from left to right. Okay, so which numbering method gives us the lowest locant numbers? Which numbering method gives us the lowest locant numbers? Red or black?
Red.
Yep, exactly right. So then we know that we have 2 methyl, we have a 3 ethyl, and we have a 4 methyl. So we name this as 3 ethyl 2,4 dimethyl And since this is 6 carbons, we call this hexane. Is my alphabetization correct? What goes first, ethyl or dimethyl? What goes first, ethyl or dimethyl? Ethyl, because E goes before M. Does this example make sense to everyone?
Yep.
Perfect. Okay, now for one with actual stereochemistry, is assuming that I didn't make another meso compound. Okay, so looking at this, is this ethyl group pointing up or down?
Up.
Up, yep. Okay, is this methyl group at carbon 4 pointing up or down?
Down.
Down, okay. And is this methyl group pointing up or down? Down, yep. Okay, so this is not symmetrical, thankfully. So we don't have a meso compound. Okay, but we will have to assign the stereochemistry. So looking at this first position, so counting off 1 carbon over, it's a tie. 1 more carbon, we see we have 3 carbons and a hydrogen. So this bottom group is priority 1. The group on the right is priority 2. The ethyl group is priority 3. So tracing from highest to lowest priority, the first center will be S. Now you may say, why am I assigning stereochemistry? Your name has to include stereochemistry. Otherwise, it's ambiguous. Okay, so to make this easier to see for these next two, I'm going to flip this molecule 180 degrees. This is rotation. I am not drawing an enantiomer. Just to repeat that, I am not drawing its enantiomer, just rotating. Okay, so now that I have this set up, I can then assign priority. So tracing 1 carbon over, we have 3 carbons and a hydrogen. So the group on the right is priority 1, the group on the left is priority 2, the methyl is priority 3. Okay, looking with that in mind, tracing from highest to lowest priority, I see I have an S stereocenter. So that's this stereocenter here. Okay, now let's look at this next stereocenter here, and let's assign priority. So tracing 1 carbon out, I see 3 carbons and a hydrogen. So this group on the left is priority 1, the group on the right is priority 2, the methyl is priority 3. Tracing from highest to lowest priority, we have an R stereocenter. So this center is R. Okay, now let's figure out our locant numbers. Let's figure out our locant numbers. So if we compare ethyl and methyl, so there are many ways of counting across this molecule. So let's look at all the methods that give us the smallest possible number. So we can do 1, 2, 3, 4, 5, 6. We can do 1, 2, 3, 4, 5, 6. Or we can do 1, 2, 3, 4, 5, 6. So which method is preferred? Light blue, dark blue, or red? Red, yep. So we'd name this as, so listing off, if this is 1, so we'd name it as 1S because position 1 is S, 2R, 4S, 1, 2, whoops, 4 ethyl, 1, 2 dimethyl, cyclohexane. Bit of a mouthful. Again, we want the lowest locant number for each of our carbons, each of our side chain substituents. Does this make sense to everyone? Any questions? Okay. So that's it for the exam. We finished the exam. It took us overall less than 2 hours. Key things to keep in mind, meso compounds. Please make sure you're familiar with the energy values for conformational analysis for both axial diaxial interactions, gauche interactions, and eclipsing interactions. And really just be meticulous when you're drawing out your structures and always just ask, is this meso? Does this have stereocenters? Do I need to worry about the stereochemistry? And really, it's recommended that you make a model because this kind of method of visualizing and assigning stereochemistry won't be going away. In fact, it'll only be getting more prevalent as we start to talk about reactions that generate stereocenters in a stereo-specific manner. So, any questions?
Could you go back up to number 2, please?
Question 2.
Yeah, question 2. I mean, I'm sorry.
No problem. Just making sure. Yes.
So I was trying to see. Can you scroll? Oh, so can you scroll down a little bit? So that's the one that you're talking about, making sure we check for the meso compounds.
Yes. It has a plane. It has a plane of symmetry and an axis of symmetry, and by rotation, these two structures are identical. And you can see that with the model if you rotate it, and you notice, wait, I've generated the same structure just via rotation. Enantiomers have a different 3D arrangement of bonds, while meso compounds are identical via rotation.
Awesome. Thank you.
Does that make sense?
Yeah.
Perfect. Any other questions that I can address? So we'll close out the recording that should be processed momentarily.